Hi, this video shows an elegant trick for computing the area A of a circle with radius r. We will use the power of calculus and compute this area with integrals. All points on a circle are described by the equation x squared plus y squared is equal r squared. We can express y as the square root of r squared minus x squared. When plotting this graph from minus r to r, it forms the upper half circle with radius r. Consider some function over an interval ab. The integral from a to b calculates the area under its graph between a and b. So integrating the square root of r squared minus x squared from 0 to r computes the area of a quarter circle with radius r. To get a, we just need to multiply the result by 4. But solving this integral sounds tricky, so let's not do that. We can simplify the situation by adding another dimension. The area A is equal to the volume of a cylinder with radius r and height 1. This volume can be calculated by integrating the constant function 1 over all points of the circle. But how does this really help? This integral still looks difficult to solve, since for different values of x, the integral range for y changes. The trick is to consider different coordinates. The classical coordinates of a point give x and y positions. In polar coordinates, each point of the circle is described by its distance r from the center, which is between 0 and r, and its angle phi, which is between 0 and 2 pi. All possible polar coordinates in a circle form a rectangle with sides r and 2 pi. Polar coordinates turn a circle into a rectangle, and this is the squaring of a circle referred to in the title of this video. After changing the coordinates, we just have to integrate the constant function over a rectangle with one side equal to r and the other equal to 2 pi. The volume of the resulting cuboid is 2 pi r. This shows that the area of a circle with radius r is 2 pi r. It is a really lovely trick. If you have learned something new, don't forget to like and subscribe. It really helps this channel. Thanks a lot for watching. That the area of a circle with radius r is 2 pi r.
Wait a second. This is completely wrong. The area of the circle is pi r squared. The formula 2 pi r calculates the circumference, not the area. What kind of trickery is this?
Great. Thanks for noticing my little scheme. We are not quite yet done. There is a mistake in the proof. And as with every mistake, we can learn quite a lot by understanding it and finding a fix. We have correctly calculated the volume of this cuboid as 2 pi r. But it is not equal to the area A of the circle. Let's ignore the third dimension and view the situation from above. The double integral cuts the rectangle into tiny pieces. Each piece contributes to the integral sum by its area. Since all pieces are of the same size, they contribute equally to the result. So the integral is 2 pi r, which is the area of this rectangle. But we are not trying to calculate the area of this rectangle. We want to know the area of the circle. Let's also display the grid of pieces. Vertical lines are mapped to rays from the center at increasing angles, while horizontal lines correspond to circles of growing radius. Let's highlight one piece in the rectangle. Since the rectangle is formed by polar coordinates, the piece consists of all points of the circle within some interval of distance r and within some interval of the angle phi. So it corresponds to a circular ring sector. If we move the piece up, the corresponding sector moves away from the center and becomes bigger. To correctly compute the area of the circle, each sector cannot contribute equally to the resulting integral sum over the rectangle. Instead, their contributions have to be scaled by some weight WR phi. Computing the area of each sector precisely would require knowing the formula for the area of the circle we are currently trying to determine. Instead, we just need a good estimate of this weight. Since it is independent of the angle phi, we simplify it to WR. Let's call the lengths of the sides of a piece delta r and delta phi. The area of the piece is delta r times delta phi. The length delta r is preserved within the circle. When delta phi is extended across the entire rectangle, its length becomes 2 pi. It corresponds to a circle of radius r, whose circumference is 2 pi r. So the length is scaled by r. Therefore, the arc corresponding to delta phi is also scaled by r. As delta r and delta phi become smaller and smaller, the sector within the circle becomes closer and closer to a rectangle whose area is r times delta r times delta phi. So WR is equal to r. Let's go back to the 3D images. The area A of a circle with radius r is equal to the volume of a cylinder with radius r and height 1. When we switch to the polar coordinates, we integrate over a rectangle with sides r and 2 pi, but the function is now r. Instead of the wrong cuboid with sides r, 2 pi and 1, it becomes a triangular prism of height 2 pi with a right triangle base with sides r and r. Its volume is therefore the area of the base r squared over 2 multiplied by height 2 pi, which gives pi r squared. Finally, we have obtained the correct formula pi r squared for the area A of a circle with radius r.
This proof is nice but quite complex. I already knew that pi r squared is the area of a circle. So what's the purpose of this video?
This video isn't meant to explain how to calculate the area of a circle. Simple proofs of the pi r squared formula exist without two-dimensional integration, polar coordinates, and fixing the proof with a geometric argument about sizes of sectors. Instead, we explore what happens when changing coordinates in integration, known as substitution. Parts of the integrated function are scaled up or down, and a correct formula must account for that. I really love this example of the area of a circle because the entire argument is geometric, with minimal computation. Additionally, people associate circles so strongly with the formula 2 pi r that the mistake is not immediately obvious. Let me know in the comments whether you have noticed the error. We will concentrate on the integral substitution for a single variable. Let's return to the example of the square root of r squared minus x squared. Its integral from 0 to r computes the area of a quarter circle of radius r. The trick here is to substitute x with r times sine of t in order to use the formula sine squared of t plus cosine squared of t is equal 1. Suppose that we could just replace x with r times sine of t without changing the value of the integral. Since x goes from 0 to r, t goes from 0 to pi over 2. Inside the square root, we get r squared times 1 minus sine squared of t, which simplifies to r squared cosine squared of t. Since both r and cosine t are positive for t between 0 and pi over 2, we can replace the square root by just r times cosine t. The primitive function is r times sine of t, and by plugging in the integral range, we find that the integral is equal to r. Since this integral should be equal to the area of a quarter circle, we again get an incorrect formula for r for the area of a circle. It turns out that we cannot freely replace x with r times sine of t without changing the value of the integral. To better understand the problem, we draw graphs of these functions for r equal to. On the left, we have the original function, the square root of r squared minus x squared. On the right, we have the modified function, the square root of r squared minus r squared times sine squared of t, which simplifies to r times cosine of t. Clearly, the area under the blue graph is larger than that under the green one. When integrating the modified function, it is cut into several pieces of equal width. Each piece contributes to the resulting integral by the product of its height and width. By mapping the piece borders using x equal r times sine of t, we get the corresponding pieces for the original function. While their heights are equal, as we go from left to right, the pieces in the original function start wider and then become thinner. It is no wonder that we get a different area when integrating each function. Again, we have to add some weight wt to compensate for the local change in the width of each piece. We call delta t the width of a piece in the modified function, and delta x the width of the corresponding piece in the original function. Recall that these two functions are linked by the substitution gt equal r times sine of t. We can plot g by placing t on the horizontal axis and x on the vertical one. For every value of t, we get the corresponding value x equal gt. A piece of width delta t is displayed on the horizontal axis, while the corresponding width delta x is found on the vertical axis. So the width delta x depends on how much the graph grows when going from t to t plus delta t. We get wt as the ratio delta x over delta t as delta t becomes smaller and smaller. Can you recognize this ratio? It is the most important ratio in all of calculus, describing how much g changes around t. It is called the derivative of g. So the weight w is the derivative of the substitution g. In this particular case, the weight wt is equal to r times cosine t. It makes perfect sense that the weight w of a substitution g is its derivative g prime. If g grows quickly around t, a narrow piece at t corresponds to a wide piece in the original function, so the weight wt is high. On the other hand, if g grows slowly around t, the corresponding piece is narrow, so the weight wt is small. The substitution in the integral of the square root of r squared minus x squared is fixed by introducing the extra weight factor wt equal r times cosine t. After the same simplification as before, we need to compute the integral of r squared times cosine squared of t. We use this formula that relates cosine squared of t and cosine of 2t. After some steps, we get the primitive function t plus 1/2 times sine of 2t. By plugging in the integral range from 0 to pi over 2, the integral is equal to pi r squared over 4, which is the correct area of a quarter circle. We have again shown that the area of a circle is pi r squared. We can compare the original graph and the correctly modified graph for r equal to. While the shapes are different, the areas under both graphs are equal to pi. This is the general formula for integral substitution. It is natural to ask why derivatives appear in this formula. I find the standard explanation using the chain rule for derivatives unsatisfactory. In this video, I have shown you a beautiful geometric argument for the substitution formula. Derivatives are not surprising here, but completely natural. This is what I love about mathematics, the never-ending search for better understanding. It should be noted that this video uses the inverse substitution rule. Substitution is usually applied in the opposite way. For example, when computing the integral of e to t squared times 2t, one can quickly find the substitution gt equal t squared and its derivative g prime t equal to t. The integral is simplified to e to x. We have explained the geometry behind the integral substitution formula for a single variable.
This geometric explanation is really cool. When I used integral substitution before, I never thought about why derivatives appear. How does this generalize to two-dimensional integrals? Do we use some kind of multidimensional derivatives?
This video concludes with a generalization for multiple variables. Let's return to the starting example of the polar coordinate substitution used to compute the area of a circle. For polar coordinates r, phi in the rectangle, the coordinates x, y in the circle are described by two functions. The coordinate x by the function gx equal r times cosine phi, and the coordinate y by the function gy equal r times sine phi. So the substitution consists of two functions gx and gy of two variables. For each of these functions, we have two partial derivatives with respect to r and phi. In total, there are 4 partial derivatives which can be placed into a 2x2 matrix called the Jacobian. The first column contains partial derivatives with respect to r, while the second one with respect to phi. When computing a partial derivative for some variable, the other variables behave as constants. So in our example, partial derivatives for r remove r and preserve cosine phi and sine phi, while deriving for phi keeps r and switches between cosine phi and sine phi. If you want to learn more about matrices and their geometric meaning, check my SoMEpi video on this topic. This Jacobian matrix describes a geometric transformation of the polar coordinates, which first scales the phi axis by r and then rotates by phi. The Jacobian describes what happens to a tiny rectangle when transformed from the polar coordinates to xy coordinates. When the size is small, it will be close to another rectangle rotated by phi with one side scaled by r. For correct substitution, we need to account for the local scaling of areas. Instead of a derivative of a single variable function, this scaling factor is given by the determinant of the Jacobian matrix. The reason is that the determinant of a matrix describes change in area when applying the geometric transformation. In this example, the determinant is equal to r times cosine squared of phi plus r times sine squared of phi, which is equal to r. So we get the same result as before. Locally the size is scaled by r. The resulting integral is again equal to pi r squared. In this video, we export a geometric explanation for integral substitution formula. The substitution locally changes sizes, and we have to compensate for this change by introducing weights. These weights depend on the rate of change and are described by derivatives of the substitution. I hope you have learned something new and have some food for thought. This video is created in the web application OrgPad I have been working on for the last 5 years. You can find a link to this presentation in the video description. It would be great if you could check OrgPad out at orgpad.info and support my work. Thank you so much for watching.